Using the first derivative, find and classify all the critical points of x squared plus x times e to the x. All right, so there's two parts to this. Of course, we're going to have to find the critical points. That's not too bad. Remember that critical points occur when the first derivative is either equal to 0 or when the first derivative is simply undefined. Now, that's not what the question means when it says using the first derivative. The first derivative part is how we're going to classify the critical points. And so using the first derivative, you can tell when a function is increasing or decreasing. And so around a critical point, if you're increasing before and decreasing after, this is what's called the first derivative test, you can conclude that, oh, that critical point must be a local maximum. And there are other criteria to test for minimums and local minimums and saddle points as well. So first thing we're going to have to do, get that derivative and figure out where it's 0 or undefined. And we do want to make sure that we check both cases. So we'll start with our function x squared plus x, and all of that is times e to the x. So taking the derivative of that, that's just going to be the product rule. We've got a polynomial times an exponential. So product rule, you leave the first function alone, and then what's the derivative of e to the x? That's right, it's e to the x. Plus, and then you switch it up. Take the derivative of the first function. Doesn't take that long to take the derivative of a polynomial, and you leave the second function alone. Now both of these have an e to the x, so we can factor that out. And so we'll have x squared. There's 1x, but plus 2 more of them, so that's plus 3 x's, and then plus 1. So there's our derivative. To find critical points, it's either when it's 0 or undefined, but in terms of undefined, we might make a little note here in red. This is a polynomial, this part here, times an exponential. Well, polynomials and exponentials are both defined everywhere, so their product is defined everywhere. So we'll say, all right, so f prime is, maybe we'll say always defined. But what that means is the possibility of getting a critical point from the derivative not being defined at a point in the domain of the original function f, that simply can't happen. Okay? But you should always consider that case. Quite often, I find that I'm running into situations where it's something that's always defined, but it's something that should be present and on our mind. All right, so the other option is, well, what happens if this is 0? And so what we got a product of two things. A product of two things in real numbers being equal to 0 means that one of the two factors must be equal to 0. Now, exponential functions are never equal to 0. Okay. You look at the graph of e to the x. It gets smaller and smaller on the left, but it never is equal to 0. You could say, well, x should be ln of 0. Well, you can't ln something that isn't positive, so yeah, that doesn't work. And so the only way we're going to get a critical point is if it's a root of this quadratic. It almost looks like this might be irreducible, in which case maybe this is a trick question. There are no critical points to classify. That can happen. X squared plus 3x plus 1 equal to 0. I can't see an easy way to factor it, but that doesn't mean we can't resort to the quadratic formula. So negative b plus or minus square root of b squared. So that's 3 squared is 9 minus 4 times 1. So 4ac, so 4 times 1 times 1, so minus 4. All over 2 times a, which is just an invisible 1 there. So that's going to be negative 3 plus or minus square root of 5 all over 2. So we have exactly 2 critical points. So this wasn't an irreducible quadratic. So 2 critical values. Negative 3 minus root 5 over 2. And negative 3 plus root 5 all over 2. All right, so these are my critical points. Which one's a local max? Which one's a local min? Which one's a saddle point? What can we do to figure that out? The question says use the first derivative, and even if the question didn't say use the first derivative, I would in this case. Okay, so just as a little sort of timeout, typically to classify critical points, there's 2 ways you can go about it: using the first derivative test and using the second derivative test. Okay. Now the question did say, yeah, use the first derivative, but so the way the second derivative test works is it uses the value of the second derivative at your critical point to figure out local max, local min. But here's the problem. That means I'm going to have to take these numbers here, like negative 3 plus root 5 over 2, and plug it into the second derivative of this, which I'm going to guess is not going to be an easy thing to calculate and work with. Okay? If the critical points were nice integers like negative 2 and 1 and 0, that wouldn't be bad. But these are not nice numbers, so I actually probably want to avoid calculating with these numbers. And the way the first derivative test works is it calculates values around, on either side of these critical points. And we can choose them to be nice integers that are easy to work with, or simple fractions, or if we're working with trigonometry, nice angle measures. Okay, so the way I'm going to do, I'm going to make a little table here. This is a pretty common way to write it up. Let's give ourselves a little more space there. And so we break up the domain of our function into 3 intervals. The values that are below our lowest critical value, the values between, and the values bigger. Now, you might be saying, well, hold on, how do you know which one's the bigger critical value? You just said these numbers are not nice to work with. So let's have just another timeout. This isn't really the calculus part of things, but let's talk about these numbers here and how we're going to pick our test values in a moment. Because what we are going to do, we'll pick a test value, we'll plug in f prime, or plug that test value into f prime, and we'll draw conclusions about f. And then from those conclusions, we can talk about the individual critical points. And so the behavior before and after, that's what the first derivative test is. But okay, let's look at these numbers. So negative 3 plus or minus root 5 all over 2. It's not an easy thing to understand what's going on here. Now, you can definitely say that this one here, negative 3 minus root 5 over 2, is negative. Why is that? Well, you can take out the minus sign. 3 and root 5, they are positive, divided by 2 is positive, so you get a minus sign. So, this one here is definitely negative. But how do I know that it's more negative or at least less than this other one here? Well, root 5 here is being added onto negative 3. Instead of taking it away from negative 3, we're adding on it, so we're adding a positive amount. So wherever negative 3 is, if you add on root 5, that brings it over to like maybe here. If you subtract root 5, that should bring it all the way over here. And then dividing by 2 will maybe move them to here and here. But one of them is definitely bigger than the other because you're adding something versus subtracting a positive amount. Right? So, okay, we've got that arrangement, but how am I going to get these test values? Remember, I said I don't want to actually be doing any calculations with negative 3 plus root 5 over 2. They're not going to be nice to plug in. So how am I actually going to get nice numbers to plug into f prime? Well, oops. Don't want to erase my number line just yet. Well, this is where we're going to stop, and we're going to take a closer look at 3 and root 5 and do some comparisons. So 5 is less than 9. It's greater than 4, and while we're at it, it's greater than 1. So root 5, square root preserves inequalities like this. So we can say root 5 is decidedly fitting somewhere in between root 9, which is 3, and root 4, which is 2. That's why I chose these numbers. So negative 3 minus root 5 all over 2. Well, subtracting off root 5 isn't nearly as big a loss as subtracting off another 3. Negative 3 minus 3, well, that's negative 6 over 2. Well, that'll just be negative 3. So negative 3 minus root 5 over 2 is over here. Negative 3 is definitely on this side. So a test value we could use that's less than that one critical point would be negative 3. Okay. What else can we say? I'll give myself a little more space here again. Yep. All right, so can we try and find a number between them, or a number that's less than, a number that's bigger than negative 3 plus root 5 over 2, which is this one here? Okay, can we find something bigger? Well, negative 3 plus root 5 isn't going to be nearly as big a jump to the right as doing negative 3 plus 3, right? Because 3 is a bigger positive number being added. And so, well, that's just 0. So we can say 0 must be somewhere over here. So 0 would be a great test value here. All right, well now, this is the one I've been sort of hesitating and hemming and hawing about. What about in the middle? Okay. Well, you definitely could say something like -3/2 is between them, because that's sort of what you start with, and you add on √5/2, and that moves you over here. So it's halfway between them. Okay. But that's not a nice number. That's 1.5, so maybe 1 is over here, but maybe 1 is actually on this side as well. So I'd like an integer. If I have to, I'll work with -3/2. That's nothing wrong. And if you were sitting there and you're saying, I'm in a rush, hurry, come on. Yeah, -3/2 is not a bad number, but maybe I can find an integer that we can work with. And so, okay, 1 is less than √5. All right, so -3 plus √5/2 is going to be bigger than -3 plus 1/2. And that's -2/2, so that's -1. Okay, so -1 is definitely on this side, but how do I know -1 isn't over here? Well, -3 minus √5, subtracting something from -3 is definitely less than adding on 1. So we can see -1 actually is going to be somewhere in the middle. I actually don't know. I suspect -2 is as well, but we don't really need it. So -1, we can definitely... we're good to go where we've got it there. So -1 makes for a good value in the middle. Again, if you weren't saying, oh, I must have integers, could have done -3/2 without a second thought, because it's the halfway point between these two. Right? Okay. So now, at long last, we can actually take these values and plug them into f prime. So -3 squared. So I'll just say that that's 9. Plus 3 times -3, so that's going to be 9 minus 9 plus 1 e to the -3. So that's going to be 1, because these guys will cancel out, 1 times e to the -3, which is positive. So my function is increasing. And then we hit that critical point. What happens when we plug in -1? Well, -1 squared is 1, plus 3 times -1 is -3, plus 1, e to the x. Right? We're just plugging everything into our f prime here, just in case we forgot it. So that's going to be 2 minus 3, so that's going to be -1 e to the -1, or -1 over e. That's negative. And so f of x is decreasing after this critical point, which means, and I like drawing the little visualization here, that means it's a local maximum. Hooray! All right, now plugging in 0. 0 squared is 0, plus 3 times 0 is plus 0, plus 1 times e to the 0, well, that's 1 times 1. 1 is definitely positive, so we're increasing again. So we're decreasing until we hit this critical point, and then we're increasing afterwards. So this must be a local minimum, right? Remember that once you have the critical points, all it takes is one value between them where the function's decreasing, and it must be decreasing that whole way, because if it were to stop decreasing and start increasing, the domain would have to be broken, or you'd have to encounter another critical point. We know those aren't the case. So there we've used the first derivative to tell us the increasing and decreasing behavior, and that gives us, that's the sort of core idea behind the first derivative test, and we are able to conclude with our little pictures that -3 minus √5/2 corresponds to a local maximum for the function, and -3 plus √5/2 corresponds to a local minimum. And that is our final answer.